I thought before going into today's topic, I will give you a 5-minute summary of what happened last time. So you guys are saying, look, looks like you got carried away with this thing. We just want to know what we need to become good doctors. Okay, so just tell us. So if you're a doctor or a lawyer, or I've had really strong students in my class who had nothing to do with any of the sciences, physics or chemistry, which is of course a great pleasure for me to know. So if you go forward into your life's mission, what should you know from the last lecture? So here's the main point. The law of conservation of energy is a powerful concept that I told you survives even the quantum revolution. So it looks like we may ascribe to systems something called the total energy, which is the kinetic energy, which is always 1/2 mv squared, and potential energy, which depends on the location of the object, and it varies from problem to problem, depending on whether you're connected to a spring or gravity and so on. In one dimension, we could always get such a potential energy for any force that depended only on location. The trick was to go back to the work energy theorem, which just applies Newton's laws and says the change in kinetic energy of the body is the work done by the body, and that work we define to be this. Then the sum of all this on the left-hand side would be the change in kinetic energy. On the right-hand side, this would become the integral of f from x1 to x2. And if f really is a function of x and not of also velocity, the laws of calculus tell you you may write this integral as the difference of two numbers. Then you rearrange the expression to get k1 plus u1. u1 is shorthand for u of x1 is k2 plus u2. And that means the energy E1 to begin with, the energy at the end. If there is a frictional force, then in this integral, you break it up into two parts, the part, say, due to a spring, and the part due to friction. The part due to a spring will integrate to give you this, then you will still have the part due to friction left over. In that case, the result will look like k1, k2 plus u2 minus k1 plus u1. Instead of being 0, will be the work done by friction. We write it symbolically this way, but the frictional force is not a function of x alone. But if you knew which path you're taking and which way you're moving, you can do that integral. You want to do this in higher dimensions. In higher dimensions, what I found out was that if you wanted the change of kinetic energy to be the work done, then what you had to do was to write this expression, which was a shorthand for fx dx plus fy dy. So you take a point and you go to a neighboring point. That's the work done, and this work done was cooked up so that it was a change in kinetic energy. Then you say, okay, let me take a finite path starting with some point r1 and going to some point r2. Then I add up all the changes. The left-hand side is k2 minus k1, and the right-hand side is this integral. This is always true. This will never be wrong. It's just a restatement of Newton's law. The problem will be, can we write this integral here as a difference of two numbers, one depending on the starting point, one depending on the ending point? Is this possible? That's a question mark. If it's possible, you're done, because you're back to writing k1 plus u1 is k2 plus u2. But I tried to convince you that it's not always going to happen. So let's understand why it's not always going to happen. It is not enough in this integral to say start at r1 and go to r2. In fact, if I just said find the integral of the work done by the force between r1 and r2, you will have to tell me, you'll have to ask me something. You agree? What will you ask in addition besides just saying start at r1 and end at r2? You will ask, what path did you take? And unless you specify the path, you cannot do the integral, because you don't know what contour you want to draw. Therefore, the answer in general depends on the path, but this right-hand side does not. So if you pick the same two endpoints and you vary that path into this one, the right-hand side doesn't change, but it's not hard to imagine the left-hand side would be different. Therefore, in general, this will not be true. So even though there's a relation between work done and increase in kinetic energy, you will not get a law of conservation of energy unless this is true. Then I said, there is still hope, because we can, in fact, manufacture forces for which this is true. To manufacture the force, you pick any function u of x and y that you like, then define a new force whose x component is minus the derivative of u with respect to x, and whose y component is the minus the derivative of u with respect to y. Then you got to go back and look at your notes and see that if you take f dot dr now, you're just adding the change in u, and when you go from start to finish, the total change will in fact be the change in u from start to finish, and won't depend on how you got there. So you're basically, what you're doing is, in the xy plane, you're defining a function u of xy, which is like a height. You define the force in a clever way so that f dot dr is the change in the height as you march. So you can start at any point on the mountain, go to any other point on the mountain. If you're only keeping track of the change in height, you're going to get the same answer no matter how you got from here to there. So you start with a potential and work out a force, and that force will then obviously give an answer that's path independent, and the potential associated with the force is the function you began with. In other words, in this problem then, k1 plus u1 will be k2 plus u2, where u is the same guy you began with. So you can get law of conservation of energy in that case. Then I told you without proof that this is the only way it can happen. In other words, we all agree that if you got a force from a potential by taking derivatives, it does the job. But I'm saying every force whose integral is independent of path will always have as its ancestor a function u, and the x component of the force will be the x derivative of the function, and y will be the y derivative. That's not obvious, but in other words, it's clear, it's sufficient, but it's also necessary. So every conservative force is the derivative of some potential in this fashion. Finally, I said, if someone comes and gives you a force and says, is it conservative or not, either you can think in your head and try to guess that function u of which this f is the derivative in this fashion. If you succeed, you know it's conservative. If you fail, maybe it's not conservative, or maybe you're not clever enough in finding that function. So here is a recipe that works for all of us. The recipe is, take that force, take the d by dy of fx, and compare it to d by dx of fy, and if they're equal, it's a conservative force. That's the summary of last lecture. How much of it detail you want to know is entirely up to you. Okay. So now, I'm going to, this is residual from last time, so I'm going to basically hide that. If you want, you can take a few moments writing it down, but you understand the point now. Point is, there are, in fact, if you think about it, it's fairly miraculous that there are forces in nature so that the work done by them doesn't depend on how you got from A to B. Even more interesting is that all the fundamental forces that we know, gravity, electrostatics, even the strong force, weak force, every force that we know, to the extent it can be described by a force, happens to be conservative. So it's not that we are hung up on some rather exceptional case. Nature is kind enough that all the forces are conservative. Now, friction is a little tricky. You might say, well, friction is not conservative, but friction is not a microscopic force. Friction is a gross average way to describe things. At some real fundamental level, every force is in fact conservative. Anyway, gravity is conservative, and then the electrostatic force is conservative also. So when we study conservative systems, we are studying something fairly general. So today I go to one of the famous conservative problems, which is the gravitational interaction. So the situation was as follows at Newton's time. You know that Copernicus proposed that the way to think about our solar system is to put the sun at the center. Now, so here is Copernicus's picture. Here's the sun. Here are various planets. You have to agree that's very remarkable. Okay, first of all, it's remarkable because that was a period when it was not publish or perish, but publish and perish. It's not a good thing to come out and say what you thought, and he still did that. Even independent of the social risk, how did anybody figure this out? Because even today, even when I know this is true, I look around, it doesn't look like this at all to my eyes. So on a good day, I flatter myself into thinking I could have maybe discovered this or discovered that. There is no way I would have done this. This is really amazing. Go out and look. Because what you're saying is, if you look at our solar system from far away, it's going to look like this. That's fine. But what is our vantage point? We're sitting on third rock, and we're going around, and we somehow think we are at rest. Everything is spinning around the opposite way. And to deduce from that chaos, this simple picture is quite remarkable. You get a lot of points just for saying this is what's happening. That was it's properly called the Copernican revolution. After the Copernican revolution, people just said, take the data we get with this as the center and transcribe it with that as the center and plot it. So the person, Tycho Brahe, was a rich guy who had his own lab and he studied the solar system, and Kepler was his assistant who carried on the work for 40 years. For 40 years, he studied this problem. Then he published his answers. I got to tell you, all of you who are going into science, I would urge you not to publish every 40 years. Okay? You're not going to get a job. You're not going to get a PhD. You're not going to get a postdoc. You'll be a 70-year-old postdoc if you do this. So the climate's very different now. Even though we have a lot more money for science, I don't think we have money for science of such long vision. The only example that comes to my mind is a work by Ray Davis, who looked for solar neutrinos for about 30 years. And fortunately, his reputation was so strong, funding agencies kept him going. He looked at neutrinos from the sun for 30 years to be really sure that there was a problem. And he confronted the theorists with the problem, and the problem subsequently got resolved. But by and large, people publish not a paper in 30 years, but rather the goal is 30 papers a year is more what we want to do. But you got to realize that we're not much smarter than our ancestors, and the possibility that we have 30 excellent ideas a year is very unlikely. So I have to admire somebody like Kepler, who after 40 years gave us something that is really solid gold, because that's what set Newton on the right path. So there are 3 laws of Kepler, okay? So 3 laws in 40 years, still better than Congress. Here is what he had. Okay. The first law is all planets go around the sun on an elliptical orbit with the sun as the focus. So I'm not going to write all the words. It'll take me forever to write it. I'm just say elliptical orbit, and you guys can get the precise text from any source you like. But I have to remind you what elliptical orbit means, right? So everyone has to know what an ellipse is. So you draw a circle, you take a thumbtack, you stick it into your table, you take a string, form a loop like that, put a pencil here, and keep the pencil tight, and walk around, keeping the distance, you get a circle. For an ellipse, you take 2 thumbtacks, and you take a string like this, keeping that length plus that length constant, and you move, keeping the string tight, and the shape you produce is the ellipse. And these are the 2 focal points, F1 and F2. Ellipse is an egg-shaped circle, and if you want to get the circle back from the ellipse, you just move the 2 focal points to a single point, and you will get the circle. Whereas a circle has only a single number, r, the radius characterizing it, the ellipse has what's called a major axis and a minor axis. And major axis 2a, and a is called the semi-major axis, which is that distance. So do you know how you can get an ellipse, why the Greeks were studying ellipses, where they come from? Yes?
If you take 2 cones and you have one as a mirror reflection of another, and you use a plane as a section to cut through
right. These are called
cones at different angles, the outline of these
right?
Circular.
There'll be ellipses, circles, there'll be various famous geometric figures. I think for our purpose, even if you took a single cone and you cut it at some angle, that would be an ellipse. That's why the Greeks were studying this. But you need a second cone for other things. But for now, if you slice a cone parallel to the base, you'll get a circle. At an angle, you'll get the ellipse. So that's the first statement. Second statement is the following. If you pick one planet, and it's there today, right? You wait a week, it's there, and you wait another week, it's there. You join these two lines, and you call that the area swept out by the planet in the first week. Then in the second week, the area swept out is that. So it's the area intercepted by the two radial vectors and the arc along which you move. And Kepler said the rate at which the area is swept out, let's dA dt be a shorthand for how much area is covered in a certain time. So you take the area swept out, divide by delta t, and he said that's a constant. And the third result is that, let me see, the square of the time it takes a planet to go around the sun divided by the cube of the orbit size is the same for all planets. That's it. These are the three laws of Kepler. Yep.
So how did you write law number 2, considering that Newton developed calculus after Kepler was right?
Well, you don't need calculus to do what I just said. Calculus says take the limit delta t goes to 0. If delta t is 1 day or 1 month, it really doesn't matter. Take a planet like Pluto. I'm going to keep calling it a planet because I'm attached to Pluto more than to some of the newer guys. You wait 1 month, you see how much area is covered, then wait another month, you will still find it's true. In fact, it happens to be true even if it's not infinitesimally. You can wait even finite periods, but this is the limit. Yep.
Are there in fact like slight deviations from Kepler's third law?
There are lots of deviations.
And those are because the orbits are exactly what they are?
No. Oh, okay. There are lots of corrections to Kepler's laws. First of all, Kepler's law, if we really observe it very carefully, none of these things will actually work. First of all, planets are not moving just around the sun. They have the pull of other planets. Secondly, the Newtonian law of gravitation, which we'll study today, has got modifications from Einstein's theory, which also modify the orbits. In fact, the truth is the planets don't follow close orbits at all, but that the ellipse, instead of starting out this way and staying this way forever, slowly rotates. And that's called the precession of the orbit. And one of the biggest mysteries was Mercury had a precession. In other words, the orbit was not closing, but like a Rosetta Stone, it was doing this. Not at this rate, but very, very slowly. The majority of that precession was fully understood by the effects that I mentioned to you, namely the fact that there are other forces on it. Jupiter, in particular, is a very massive planet. You cannot ignore this effect. But still, there was a tiny part that was missing, which is 43rd degree of an arc per century. Very, very small deviation left unexplained, and the general theory of relativity filled in that gap. So the answer is, every law I told you long back will receive corrections, but they're usually very small. Anyway, this was the data that was given to Newton. So Newton, as you know, was sent home from college because there was a plague. And he went and lived in his old village, and he was contemplating this issue because he had already, by this time, invented the laws of motion. And I think he had also invented the basic ideas of calculus. There is some debate about who got there first, but there is no debate about what happened next. So Newton said, okay, I'm going to understand planetary motion. And so are you. So you guys have been terribly disappointed that after all the work you put in, you're still doing inclined planes and pulleys and whatnot. So today, we're going to make a big leap. Today, you're going to understand how planets move around the sun. That's the mega problem, right? the little m's you put in the equation are not mass of a pulley or a plane, but mass of Jupiter or mass of the sun. So you're doing something of cosmological proportions. And you don't need to know too much more to do that. Okay, you're almost there. So I'm going to just tell you the one missing thing. So what Newton had done is to realize that in order to understand motion of bodies, you have to associate a force with acceleration and not with mass. That was his contribution. If you think it's forces that cause velocity, you look at a planet going around the sun, where the velocity is pointing in different directions at different times, and you have to ask, what can possibly be propelling the planet in this loop? You don't get any definitive answer. On the other hand, if you calculate the acceleration of the planet, take the simple case where the planet is going on a circle, the acceleration at every instant points towards the sun. Okay? That's why it's important to understand what forces are doing. Forces are causing acceleration. So Newton had already showed us, and we have done many problems, when a body accelerates, there's a reason for it. Well, all bodies are accelerating towards the sun. It's fairly clear what the reason is. The reason is the sun. And you then postulate a force that's exerted by the sun on the planet that bends it into a circle. And your job is to find out that force. What's the nature of the force? So it is again here that Newton decided that the force that bends the planets around the sun is the same as the force that bends the moon around the earth. It was known by then the moon is also going around the earth. So let's look at that problem. So here's the earth, and here is the moon, and it's going around the earth. Now the moon is accelerating towards the earth, and that's something we have learned in this course. Then here is the famous apple, also accelerating towards the earth. And Newton decided that the cause behind both the forces is a new force, the force of gravity, the same thing that pulls the apple as what pulls the moon. So we have to now ask, what is the nature of that force? We're going to write a formula for the force. First, let me look at the magnitude. The direction is very clear. It is directed towards the center of the earth, so I won't write that down. Later on, I will write you a formula with vector symbols in it, so the vector will point towards the center of the earth. But let's look at the magnitude. If you take an apple here of mass m, and you call big M the mass of the earth, near the earth, we all know the acceleration of a body is constant. Therefore, it can happen only if the force depends on the mass of the apple. This force is going to depend on various things. I'm going to write the formula, but one thing it depends on, it's got to be proportional to the mass of the apple. That's because then if you divide by m to get A, the mass drops out, and you understand the fact that everything near the earth falls at the same rate. The only way that can happen is if the force depends on the mass of the apple. You agree that that m belongs there. Okay, if it doesn't belong there, if you have something that depends on m squared, for example, or doesn't depend on m at all, you have a problem. If the force doesn't depend on the mass at all, suppose the force on every body near the earth was a constant force, then when you divide by mass, you will find that heavier objects will have a smaller acceleration, but that's not what you find. So that's a perfect and precise cancellation on the mass of the object. All things follow the same rate, so I know I need this m here. What else do I need? You notice that from the third law of Newton, if there's a force on the apple must exert a similar force on the earth. So if you take an example in which here's the earth and here's the apple, there's a little m sitting there, but imagine the apple's getting bigger and bigger. Okay, the formula is not going to change. Make it bigger and bigger and bigger and bigger till it looks like the apple is that big and the earth is that big. Then you will have to agree that from that point of view, you should also have the mass of the earth here playing a symmetric role. So these two masses have to be there. But then what else should I have there? I mean, what are the other variables in the problem? Yes? The distance between them, and I don't know what the distance dependence is. I'm going to say that it's some function of the distance between them. So we don't know what the distance is. All right, so let's find the acceleration of the apple. That happens to be the mass of the Earth, this function with r calculated to be the radius of the Earth. Then you go to the moon and you ask, what's the acceleration of the moon? It's the mass of the Earth times the same function at the radius of the lunar orbit. Does anybody know how far the moon is? Any guess? You know how far it is? Make a wild guess. Million miles. Not bad, but not quite there. Any other guess? Yes?
250,000.
Pretty close. 238,000 miles. So that's 250,000 miles. So million's not bad. Okay, if you make an estimate that's off by a factor of pi in physics, it's fine. But if you say 10 miles or something, then we should have a talk. We should have a very long talk after class. Okay, so that's correct. So this guy is 240,000 miles, just to be simple. The radius of the Earth, how about that? Yes?
6 times 10 to the 6 kilometers.
How about in good old-fashioned miles?
3 times 10 to the 6 miles.
10 to the 6 would be a million miles. Okay. Anybody have a quick answer to how many miles? What's the circumference of the Earth? Okay, then you can do the math and find out the radius. Okay, 2 pi is like 6. So radius is 4,000 miles. So this is 4,000 miles. And this is 240,000 miles. Look, I know that we should work with meters and kilometers, but like the rest of you guys, once I get on the freeway, I'm watching how many miles per hour I'm driving, not meters per second, because I have no idea what 55 miles per hour is. So we do use a lot of British units. If you go buy insulation at Home Depot, it's in BTUs per slug, per poundal, per something, right? So we still do that. So in some sense, you wonder why you had the War of Independence if you're still using those units, because that's about the worst part of the whole system. But we still use it. So my brain is split. When I do physics, I use the metric system. When I go to Home Depot, I use the Home Depot units. Okay. All right, so here is the two accelerations. Let's take the ratio of those two numbers. Now, Apple's acceleration, all of you guys know, right? It's the one thing we know from day one, 9.8 meters per second squared. Acceleration of the moon, how am I going to find that? So I need an idea on how to find the acceleration of the moon. Anybody from this corner of the room on the top? How do I find acceleration of the moon towards the Earth? What do I have to know? Yes? Very good. That's what all I wanted from you. We'll fill in the blanks, but it's v squared over r, and r is this 250,000 miles, and v is the orbital velocity. Now, you may not know the orbital velocity of the moon, but you know it goes around every 28 days or something, right? So velocity is 2 pi r over 28 days. Put it into seconds, you get some acceleration. Yes?
Are you assuming that the orbit is a circle?
Yes.
Is that why you can use v squared over r?
Right, exactly. In fact, if it's not a circle, it's much more complicated. So in this calculation, we'll assume everything is a circle. It turns out to be not so bad even for planets. So if you do the v squared over r, you put the numbers in, and you find the acceleration of the apple is 3,600 times more than the acceleration of the moon. On the other hand, you find the apple and the moon radii are a factor of 60 apart. In other words, the moon is 60 times as far from the center of the Earth as the apple. And you look at 60, you look like 3,600, right? You don't have to be a Newton to figure out what's going on. Then you therefore write down this great formula. Do you understand now that r square, how you get the r square? Again, it's pretty remarkable because this could have been r to the power 2.001, and you would certainly not know you're wrong because these numbers are not known that well. Newton just said, look, let me take the nearest integer power. It looks like close enough to 1 over r squared. It happens to be 1 over r squared is a fantastically good approximation to the law of gravity. So we were also quite fortunate there. The laws of gravity didn't have to be that simple. Okay, so now are we done? Or should I do something else to this? Pardon me? This is the force. I need what else now? One of you have to put your hand up and take a stand. Yes, you have to say something?
Constant.
A constant. Right. Why do you need the constant?
Because if you just multiply what we had on the board, we probably wouldn't get exactly that answer.
Very good. Yes?
If you look at the units, the maths are
Okay, units don't match, right? So if some kid called Isaac comes to you and says, I got this new law of gravitation, I'll say, go back and fix your units. Units don't match. But not only that, I think some of you had another objection, that if you took the mass of the earth and mass of the moon, the apple, and divided by the radius, you will get a number that won't agree with the force of gravity near the earth as we know it. So the point is, when a function is proportional to all these things, there is always a proportionality constant. And the constants, one of the purposes of the constant is to make the dimensions come out right. Other is to make the values come out right. Because I got to make sure that when I apply it to an apple near the earth, I put the mass of the apple, let's say divide by the apple. This whole thing, what should it be equal to? It's got to be 9.8. You understand that? The acceleration of the apple near the earth has to be 9.8 if I put the radius of the earth here. This better be 9.8. So you pick a number g, which is some number, 6 times 10 to the minus 11, and the units for g are some number times Newton meter square over kilogram square. That will make the units come out right. So that's called the big G. That's the gravity. This is a law of universal. It's a universal gravitational constant. I'm almost ready to write down now the great Newtonian law. The great Newtonian law says F is equal to G m m over r squared, where these are two objects of mass little m and big M at a distance r from each other, but it's not yet a vector. This is just a number. So I want to say that if this is one mass, here's the other mass, I want to say this one feels a force towards the center. So let me take the earth to be the center here. I want the force on the moon. I want a vector pointing towards the center. So I know one vector that's pointing away from the vector, which is the position vector r. But if I divide that by the length of the position vector r, I think all of you know enough vectors to understand this vector has length 1 and points away from the center. But I want it to be pointing towards the center, and that is then the force of gravity on the moon or on the apple or any object. If I'm thinking of one fixed object like the earth, this is the force on the apple. If you're thinking of two objects of comparable size, you will have to say the force on one due to the other. Okay? When you write the formula, then you've got to make sure that the force on one is pointing to the other one and force on that guy is pointing towards this guy. So there is no universal symbol for all those things. I will write it in the simple case where we imagine at the center some massive object like the sun and something tiny going around it. Then the center of coordinates is chosen to be at the center of the massive object. This is the force on the little guy. This is the law of gravity. It's called the law of universal gravitation because it really is universal. You got to realize that was a tremendous leap of faith to believe that the laws that are operative near the surface of the earth also apply to the moon and also apply to the planets. This was the year 1600 and something. There was witchcraft and people had all kinds of superstitions. People are not even thinking in scientific ways. There are a lot of illusions about what the heavens are made of. To believe they're made up of similar stuff and controlled by the same laws, that's very obvious now, but it was very far from obvious in those days. It's a tremendous leap of faith. And luckily for us, that leap of faith is justified because the laws of gravitation, in fact, the laws of physics that we deduce near the Earth, seem to work all over the entire universe. If you've seen pictures in NOVA of where we are in the scheme of things, we are in a very tiny part of the universe, sampling a tiny volume over a tiny period of time. But we apply those equations to the far end of the galaxy, the far end of the universe, and going all the way back to Big Bang. And we predict the future fate of the universe. So we assume that the laws that we discover here, now, are valid everywhere and at all times. So far, that seems to be true, and that's a big break for us. But for that, you really couldn't do anything. If the laws you discovered today are not valid tomorrow, you cannot make any predictions. So it's another unwritten benefit we got. I mean, unspoken of, but it's a great benefit that the laws you find are universal. But somebody had to stick his neck out and say it. This is one of the first occasions. So now you're going to apply this law to understand what Kepler did. Okay, so what do you have to do what Kepler did? So we're going to consider the motion of a planet around the sun. So let's put the sun here. Let's put the planet here. The planet's at a location R. You go back, as usual, to the only equation in town, F equals ma. Now, F, I told you, has to be deduced every time with painstaking experimental data. Without that, F equals ma is useless. If you don't know what's on the left-hand side independently, let me repeat again. You don't say the force on the body is ma. Force on the body is due to a spring, due to gravity, due to charges, whatever. You have to do some work to find this. Then you put it into that equation. So let's put in here, the right-hand side of Newton's law can be written once and for all. d to r, now I'm writing d to r over dt squared because I'm living in two dimensions. Now on the left-hand side, I have this new result, gmm over r squared times, I'm going to use a symbol r hat, which is very common. R, anything with a hat on it, is a vector of unit length pointing in the direction of the regular vector r. So if you want, if r is the position vector of an object whose length is r hat is a little guy whose length is 1 and which points in the radial direction. So this is your equation. It's then a problem in calculus to solve the equation, and everything Kepler said should come out of that. You should find planets like to move in elliptical orbits. You should find the area swept out as a constant. You should find the square of the time period is proportional to the cube of the orbit size. Now, if I give this to you as a homework problem in the class, I dare say it will be very difficult for most of you. I don't know what kind of background you had. You have done some calculus, but it's not easy. But remarkably, Newton also solved this problem. Even now, when I teach it in physics 400 and something for advanced mechanics, it takes a while to know how to solve this equation. It's one thing to write it down, another thing to actually solve it and get the ellipse out of it. So Newton did that too. So it's really amazing. That's why he's such a giant. I mean, you have to step back to that period in time and ask, what did one person accomplish over a period of about 5 years? So that was how physics is always done. Somebody looks at the data, sometimes summarizes the data in the form of certain phenomenological facts, like the laws of Kepler, then somebody else has to, like a theoretical person, has to figure out what is the underlying rules of this game, write it in mathematical form, and solve the mathematics and verify it. Just imagine that you wrote this equation, but you couldn't solve it. What you would be saying would actually be correct. You, in fact, have found the correct law of gravity, but you can never be sure it's right because you cannot find the consequence of your equation. That is not unheard of. That's happening in physics today. For example, there's a theory of quarks. The quarks are attracted to each other by a certain mechanism we know. We know the underlying force law. And from that, we're supposed to understand the existence of all particles, like protons and neutrons and so on. We do not yet have a way to show without any doubt that the underlying equations imply the phenomenon that we see when we apply it to the problem of quarks. By putting it on a big computer, we are fairly certain that's correct. That would be like solving Newton's laws on a computer, but what Newton did was didn't solve it on the computer, but solve it analytically. So quite often, in the past, whenever a theory is accepted, it's because the consequences can be worked out and compared experiment. But you could be in a position where you have the right theory and the right equations, but you cannot solve them. Anyway, this one happens to be solvable. If I change the force law to 1 over r to the 2.1, then it's a different story. Anyway, so we want to solve it, but we cannot do the ellipse. Okay, it's too hard. So we are going to do the circle. We're going to take orbit to be circular, and we're going to apply this force law to that and see what we can get. So let's do that. We could ask ourselves, can a planet have a circular orbit of radius r? We go back to F equals ma. Now, you guys are expert on the right-hand side now. We are assuming the planet moves around the circle at constant velocity, at constant speed. We want to ask, can such an orbit exist? You're always allowed in an equation to make an assumption and plug it in and see if it works. If the left-hand side and the right-hand side match, you win. Nobody will ask you any more questions. So we are asking for a modest goal. Can I find an orbit of a planet going around at constant speed around the sun on a circle? Let that constant speed be v, then ma, everyone seems to know, is mv squared over r. And it's pointing towards the center. That should be equal to the force pointing towards the center. And Newton has told us what the force is. It's g mm over r squared. Everybody understand now? The left-hand side is the effect, the right-hand side is the cause. If you're spinning a rock, spinning it in a circle, that also has an acceleration toward the center, but the string is providing the force. And you can work out the force of a spring, of the string. Here, it's the unseen force of gravity from the sun reaching out the planet and pulling it in. Newton tells you the formula. Deduced from terrestrial and lunar observations, now applied to planets. Okay, so this is something that should make you very happy because it's a very simple application of F equals ma, but you're describing planetary motion now. So these are all masses of big guys, the Earth and the sun. So let's cancel the r, and I get, cancel the mass. That's very interesting. So that says v square r equal to gm. It says, yes, you can have a circular orbit at any radius you like, provided you move at a speed satisfying this equation. And as long as you satisfy the equation, I don't care if the thing that's spinning is a satellite or a potato, because the mass of the object drops out. So the condition for orbit is independent of the object orbiting, again due to this cancellation of the mass on both sides. All right, so this is all we can get out of Newton's laws, and let's go back to Kepler. Is the orbit possible? Well, if you say an ellipse, a circle is a special case of the ellipse, you have shown circular orbits are possible. How about equal areas in equal time? It's obviously true in this problem because it's going at constant speed. If it goes that far in 1 week, it'll go that far in 1 week, and everyone can tell the area swept out is constant. So the only thing left to knock off is the third assumption, the third observation of Kepler involving the time period. So I do the simplest thing. I say the velocity of this planet is 2 pi r divided by the time period. I put that in here, and I get 4 pi square r cubed over t square is gm, or I find r cubed over t square is equal to, let me write t square over r cubed, because that's how Kepler wrote it. This says t square divided by r cubed is equal to 4 pi square over gm. So that's another result you got right away. That's the third result, that the time period and the orbital radius. Here is, what did Newton do that went further than Kepler? Can you tell me what he did that's a little beyond? Have you just verified Kepler's laws, or have you gone a little beyond that? Yep.
Well, Kepler says that t squared over a cubed is always the same, but Newton defines why it's
Exactly right. Let me repeat what he said. Kepler said t squared over a cubed is the same thing, but he didn't tell you what the same thing is. What is the constant? Well, now we know that constant to be 4, known to all of us, pi, known to all of us, m, mass of the Earth, and g, mass of the Sun, and g is the universal constant of gravitation. So you calculate the value. Similar thing happened in atomic physics. A high school teacher called Balmer was studying the spectral lines coming out of an atom, and they were coming out at different frequencies. And he said all the frequencies you'll ever see coming out of an atom look like some number times 1 over 1 integer square times 1 over a different integer square. He didn't know what the number was, but it's some constant. I mean, he knew the number, but he didn't know. He knew the number, but he didn't know where it came from. When Bohr had his final theory of the atom, it had exactly this form, but this was just not simply a constant you put in. It involved pi and the electric charge and the Planck's constant and everything. So Balmer did for Bohr what Kepler did for Newton, which is to condense complicated data into some simple form so that a theorist can have a go at it. Then once you got the right answer, it's really beautiful how everything fits. So we know this is right. Okay, this is called a theory. By the time physicists will call something a theory, they put it to a lot of tests. Okay, it's not to be casually used. And you have the right theory, you can make a lot of predictions. You can have a theory the planets go around the sun because some angels are flapping their wings. And I say, where are the angels? You say, well, part of the theory is you don't see them. It's very good. What's your next prediction? Tell me when the next eclipse is. Tell me if the meteor headed for Earth is going to hit or miss. Is this comet going to reappear, or is it a one-shot thing? If you cannot answer any of that, you don't have a theory. You have an interpretation of past data that coincides with past data. That's worth nothing. Okay, so here's an example of how to do it right. Okay, so this thing has got enormous power. It tells you if you find another planet, you find a new planet tomorrow. If you know how far it is, I'll tell you what a year is in that planet. I'll tell you how long the planet takes to go around the sun, because t squared over r cubed is known to me. So if that planet is at a certain distance, I can tell you the time period, or if I see it going around the sun and I know it's going to complete a revolution in 240 years, I can tell you how far it is. So that's another power of the theory. Okay, so now you can do a variety of problems using this formula. They're all plug and check, but I'll just mention one, and most problems are like that. Everything is going to be plugging into this formula. But one interesting example is the following. So here is the Earth. I'm here, and I want to watch a tennis game being played there. I have radio waves, but you know radio waves cannot go through the Earth. They can only travel in straight lines. And the answer to that, I think all of you know, is to have a bunch of satellites, 3 of them in particular, forming a nice triangle. And if you can talk to this satellite from where you are, that satellite, with the help of the other 2, can always hit any other point you want, just by bouncing off. Okay, you bounce off this, you can go there, and you can hit this guy. So if you have 3 satellites, they can help you connect any point on the Earth to any other point by reflecting off the satellites. But the important thing is the satellites better be where you think they are. They're constantly moving around. It doesn't work. So what you really want is what's called geosynchronous satellites. They are satellites. Remember, if I look at the Earth from the top, it is spinning. This is the North Pole, and it's spinning. Therefore, these satellites should be rotating around the Earth once every 24 hours. Then, if they're on top of your head today, they'll be on your top of your head all the time. Right? So the time period of the satellite is 24 hours. Then the only question is, at what altitude should I launch them? You go to this formula. Put in 24 hours, write it in seconds, you will get the radius. And once you got the radius, this equation will tell you at what velocity they should be put into orbit. That's it. That's how you put the geosynchronous satellite. That's a simple example of applying the formula. I won't give other examples, but they're always going to be finding t from r or finding r from t. Sometimes you will know r, sometimes you will know t. Any question about this? Okay. Now I'm going to come to the question of energy. whenever you have a new force, you can talk about the law of conservation of energy. So I want to ask myself, what's the potential energy I can associate with the gravitational force? I can ask myself, is it even a conservative force? So let's take the problem in two stages. First of all, if you're near the Earth, everything falls down near the Earth. If that height is y, then the force of gravity is minus mg times j, where j is the unit vector in that direction. The potential energy is then mgy, and everybody can check that if you take the minus the y derivative of this, you get the force. That's the potential energy, and therefore when a body is falling near the surface of the Earth, we may assert that 1/2 mv squared plus mg, let me call it height instead of y. Let me call this coordinate h instead of y. I don't think it matters too much. That is the total energy, and that is a constant. We applied it the other day to roller coasters, going up and down, speeding up and slowing down. It's just that this number will not change. As the roller coaster changes the height, the speed must change, keeping this number constant. But you know, this formula is an approximation near the Earth. We want to apply it globally. Before going to the global problem, let me remember one more thing, that G is equal to Gm over Re squared. Because when you apply Newton's law to the surface of the Earth, you better get this number G when you apply it to something near the Earth. By the way, Newton took a long time to publish this law of gravitation. Does anybody know why he was holding back for a long time? Have you heard anything? Yes?
Newton was in the controversy over the discovery of the calculus with Leibniz, and then I think Edmund Halley convinced him later on.
Edmund Halley may have convinced him to publish, but it was something else that was bothering Newton. Yes?
He was afraid of criticism?
He's afraid of criticism. Maybe, but that was not why he held back. Yes?
Did he also doubt it very much?
Pardon me?
Didn't he also doubt that it was impossible?
No, but look, when he applied it, by the way, he applied it to everything. Celestial motion, to the behavior of tides, everything seemed to work. There is one further assumption that you make. When I wrote 1 over Re squared, I said the distance of the apple from the Earth is that. Or maybe it should be just 2 meters from which I release it. Somehow he knew you have to measure the distance from the center of the Earth. So it is not clear for the purposes of gravitation. In other words, originally Newton had a law of gravitation between 2 point objects, namely the point like, the distance between them is unambiguously the distance between the points, and he got this law. But in the end, he wants to apply it to the Earth and the apple. They are close enough for you. You cannot pretend the Earth looks like a point from where I am. It looks like a big fat thing. You cannot say it's point-like. So what you really should do is divide the Earth into tiny pieces, each one of which is point-like. Find the force on from each chunk of the Earth using this law and add it up. And if you're lucky, it will look as if all the pull is coming from one point at the center, carrying the entire mass of the Earth. So what branch of mathematics do you have to use to get that result? Yes? What branch of mathematics? What kind of calculus? Had it been invented? No. So he had to then invent integral calculus also. So, if he felt that no one around him was doing any work, probably justified, because they just dumped the whole thing on this kid and said, why don't you do integral? That's why it took him a long time to verify, using integrals, that the sphere behaves like a point particle at the center. He knew it works because all these numbers couldn't be all the coincidences or not coincidences. He believed it worked, but he had not found a way to show it. And that's what held back a publication. Okay, that's another rare behavior. Okay, anyway, I come to this problem and I say, I want to apply it not near the Earth, but arbitrarily far. Near the Earth, the force is minus mg, but far from the Earth, many, many miles away, the force is really what we wrote here. It's minus g m over r squared times r unit vector in the radial direction. First thing you can check is that this is actually a conservative force. I'm going to give this to you. I don't have time to do that. In other words, write this capital R hat, if you like, as an R divided by one more R in the bottom. We don't care. And that can be written as minus G M M times I times X over R cubed plus J times Y over R cubed. Right? I just wrote the vector R in terms of X and Y. So the X component of this force is X over R cubed. The Y is Y over R cubed. R is just square root of X squared plus Y squared. So maybe you can tell me, what should I do to check that this is a conservative force?
Use that formula you showed us at the beginning, the partial derivative.
Yes. So I will repeat what he said. That's the correct answer. I must take the X component of this, take the Y partial derivative, the Y component of this, taking X partial derivatives. You guys should do that. When you take the derivative of something like 1 over R cubed, you should first take the R derivative of R cubed and then take the X derivative of R or the Y derivative. Using the chain rule of calculus, you will find the two agree. So we know it's conservative. That's the power of the result. So all you have to do is guess what potential could have led to this force. So I say, okay, let's put the sun here. Let me move along the x-axis. The force along the x-axis look like minus G mm over x squared, because x is just r if you're moving in this direction. In other directions, that's r, but let me just move along the x direction. I ask myself, what function has a property that minus the derivative of that with respect to x looks like this? That's a Mickey Mouse calculus problem. It's just minus 1 over x. Okay? Derivative of minus 1 over x is minus 1 over x squared. Therefore, x is r. In general, the u that you want for gravitation looks like this. So gravitational potential energy for problems arbitrarily far from the center of this mass, not near just the surface of the Earth, but wherever you go in any gravitational problem, this is u. You can check that if you took this u, it's what I'm telling you guys to do. If you're really careful, did I miss something?
Shouldn't that be positive?
No. Let's see. If you took the r derivative of this, 1 over r is r to the minus 1. Derivative of that will make it plus 1 over r squared. But you're really supposed to take minus the derivative of u, and that will be the right thing. So this is the potential energy, which will be negative. So what am I claiming? I'm claiming that if you got the sun and you got some other planet moving around it, the following quantity will not change, which is 1/2 mv squared minus g mm over r is a constant. Now take an object moving near the Earth. I gave you a different rule. I said near the Earth. What did I say the rule was? The constant is 1/2 mv squared plus mgh. Kinetic energy looks right. Potential energy looks really wrong. There seems to be two definitions of potential energy. They don't even agree in sign. So what's going on? What's the way out of this problem I am in? You have any idea?
Substitute G by somewhere there.
Big G, you mean? Or little g?
No, little g by the formula we derived for.
Oh, that's not a bad idea. Suppose I do that. That's a very good idea. So let me write that as G M M over R E squared times H. That's a good plan, but you notice this cannot possibly equal that because that's negative, right? This is positive. Any way to reconcile these? Yes?
Well, the difference is because the first one is for different values of force, while the second one is assuming a constant.
I agree. But no, one doesn't. The constant is certainly, it's true that near the Earth we treat it as a constant. But if I took the formula valid for every distance, and I specialize it to the problem near the Earth, it's got to agree with the problem near the Earth, right? The bigger formula should embrace or enclose a smaller formula.
Maybe we should set, the radii equal for the first one.
Yeah, I will do that. In other words, I grant you, I'm willing to put RE here, right? But there is no way this expression and this can match because they're not even of the right sign. You don't even have to think more than that. They cannot be right as they are. Yes?
Maybe try to explain h in terms of radii, like it's a difference in...
No, h is the number of meters above the ground. You put the number in. Look, most of your escape routes don't work because you're trying to get a positive number to equal a negative number. Yes?
It depends on where you set your judgment.
Thank you. I didn't know I was going home for lunch because I was not going to proceed till I got the right answer. The right answer is when you define a potential, there is a freedom to add a constant to the definition of the potential. If you look at every theorem, everything I derived, including the stuff I hidden under the board, U1 minus U2 is what enters everywhere. The change in kinetic energy is U1 minus U2. Therefore, one has a freedom in defining the potential to add a constant. And what has happened is that the person working with this potential and the person working with this potential have not taken the same reference point. This person working near the Earth said, let me choose for convenience the potential at height equal to 0 to be 0, because that's a natural point for me. What about this person here? Yep. He's saying potential is 0 at infinity. Because when you're doing celestial mechanics, here is one object, other object at various distances. Infinity is a rather interesting point. You go infinitely far from it, no potential energy. So the two of them differ by a constant. That's the reason why. And the constant can easily overturn a quantity that's negative and bring it up to positive values. So except for that constant, once I add a certain constant, everything should work out. So I will show you that it does. Okay? Then everything will be fine. Maybe there are two ways to do it. I'm in two minds on how to show the two ways. I'll try one method. Let's take the answer that's valid for all distances. Right? That's the celestial formula. Forget all the constants. It looks like minus 1 over r. You agree? Some blah, blah, blah constant divided by r. So it's a graph that looks like this. It blows up to minus infinity when r goes to 0, and it goes to 0 when r goes to infinity. This is the formula for u for a person who says u is 0 at infinity. Now, let's look at the formula in the neighborhood of the surface of the Earth. Here is where we are most of the time. So, if I shift my 0 to here, then by design, I've made u to be 0 on the surface of the Earth. Then let me also measure a new coordinate this way called h, which is the radial distance away from the RE. This is RE, this is RE plus h. Then I blow up this box. What do you find? I blow up the box with my newly shifted origin. Here is h, and here is the potential energy looking like a straight line. And if you're lucky, the slope of the straight line should be what? What should be the slope? So we can reconcile everything. If a function is a straight line, it has a certain slope. What's the y coordinate? Slope times the x coordinate? Yes? Not g. Yes? mg. If it's mg, if that's a slope, mg times h would be the function you're drawing. Right? So that's all I have to show you. And I will show that that's what happens. Then we're set. So let's take the master formula for the potential energy. Write it as gmm. Let's apply it to a distance near the Earth, which is r plus h. That's what we're trying to do, right? Now, so you massage that expression as minus gmm over r times 1 plus h over r. That is just a rewriting of this. And you can write that. I'm sorry, apologize. Do you know what's wrong with what I wrote? This is not r plus h. What should I be really putting here? Radius of the Earth. So I don't know how you're going to correct it in your notes, but this really should be radius of the Earth. Everywhere here, I want to be at a height h above the radius of the Earth. So I put that here. Then I write this as minus g m m over radius of the Earth times 1 plus h over radius of the Earth to the power minus 1. I just bring the downstairs to the upstairs. Then remember the wonderful formula I told you. You guys have to know this. 1 plus x to the n is approximately 1 plus nx if x is very small. X is here the height over the radius of the Earth, which is obviously tiny. So I can approximate that, and I get u equal to minus g m m over re times 1 plus g m m over re squared times h. This is the potential energy at the surface of the Earth. For a guy who thinks it's 0 at infinity, this is the change in potential energy when you move a distance h. Therefore, if you calculate u of h minus u of 0, you will cancel that term, then you will get the same answer as the person using this formula. So that's very important to understand how these two are saying the same thing. It is best understood in terms of the graph that I've drawn for you. You shift your origin to one place, and you also shift the zero potential to one place. Now, for a circular orbit, what's the energy? It's 1/2 mv squared minus g mm over r. But we know that 1/2 mv squared is v squared is equal to mv squared is a centrifugal force, the centripetal force, and therefore you can write that as g m m over r minus g m m over r. You find the answer is then minus the potential energy over 2, or potential energy over 2 r minus the kinetic energy. In other words, if you combine these two terms, you get minus g m m over 2r. So for a particle in a circular orbit, the kinetic energy is exactly half the magnitude of the potential energy, and the total energy is negative. Okay, so I want to close with one very important result. So whenever you see a celestial body, here's the sun, you see some celestial thing moving around, you can compute the total energy. If the total energy is negative, that object is bound to go on orbiting the sun and can never escape to infinity. The total energy is positive, it can go to infinity. And 0 is the borderline case. So why is it that if the total energy is negative, the body can never run off to infinity? Can anyone think of a contradiction you would have if a body of negative energy found itself at infinity? Yes?
I mean, it will have to gain energy to go to infinity, because then the potential energy will be positive, like 0.
No, at infinity, potential energy is 0. What about kinetic energy? Some positive number, right? But its initial energy was negative, and you cannot change it. So if you got total negative energy, you cannot be found wandering around infinity. Because at infinity, if you're moving around, you got positive kinetic energy, no potential energy, and your energy was originally negative, you have no business being there. So objects with negative energy will never escape. So if you saw a comet, you want to know if it will come back again, find the kinetic plus potential. If it's positive, it won't come back. If it's negative, it's trapped. That's the dividing line. So if you're near the Earth and you want to shoot something, you can pick it in any direction you want. Suppose you start shooting them up. They go to different heights. And one day you don't want it to come back. You can ask yourself, how fast should I fire a gun so the bullet never comes back? Well, you should fire it so that it can go to infinity. when it goes to infinity, you want to just manage to get there. It's going to go to infinity, stagger, and fall down. Well, it's got no kinetic energy at infinity. It's got no potential energy at infinity. Therefore, its total energy should be 0. Therefore, what you should do, at the surface of the Earth, your 1/2 mv squared minus gmm over r Earth should be 0, or these two numbers should be equal. Or canceling the mass, you will find some formula, which is v squared equal to gm 2gm over r e. So depending on the mass of the Earth and gravitational constant radius of the Earth, you'll get a velocity. That's called the escape velocity. When something is fired with escape velocity, it will just about make it infinity. You want to be really sure it doesn't come back, give it a little extra speed. A little less, it'll orbit the Earth. It just won't go away. All right, so I want you to think about what you've learned, because if you can now go and read articles. For example, you heard about dark matter. I'll just tell you one sentence about dark. Anybody heard about dark matter? Okay, most of the universe seems to be made out of stuff we cannot see. Okay, you, me, we don't add up to anything. Very small percentage. How do people know that is dark matter? You cannot see it, but you know it's there. How do you know it's there? You know it's there because our galaxy, or any galaxy, has got matter you see and matter you don't see. If you draw an orbit around the galaxy, going all the way around the galaxy, you can treat the entire mass as sitting at the center. Then you can use your gravitational formula, v squared r is the enclosed mass. If you go further out, you should find you're not enclosing any more mass, because the mass is all what you see. But what we find is, as the orbit gets bigger than the galaxy, v squared r keeps on increasing, so the mass enclosed is increasing. But you don't see it. That's how we know there is mass, which is not visible to visible observation. But every galaxy seems to have this halo of dark matter. That's how we estimate the mass, and it beats all the known mass. But you can do that using just this calculation.